Hey everybody, Thrasher here. In this video, we are getting into electric fields, kind of an expansion from gravitational fields, which we saw earlier. Now we learned a little bit about the atom and charges that are associated with particles within atoms. So let's first remember some core physics in this video, okay? First, we saw that charges from just a prior video ago, charges can attract or they can repel. We learned that protons have a positive charge, electrons have a negative charge, and depending on what charges you have, sometimes they attract, sometimes they repel. Well, let's think about that for just a moment. If I have a negative charge and a positive charge, let's say I could hold on to them with tiny tweezers. If I then let go, and those two charges, because opposites attract, they then started zoink moving towards each other, everybody, that means the charges are accelerating. And that's actually really important because what physics term did we learn is required to make objects accelerate? Team, that's a force. So by deduction, if we have charges that sometimes attract, sometimes repel, that means these charges are accelerating, which must mean there is a force involved. Okay, so there are forces that are acting on electric charges. Now, team, if you keep watching this animation, are they attracting because like there's a string between them that's getting pulled? No, there's no cable. There are no like giant hands appearing and smushing them together. This is a force that is seemingly acting at a distance, no contact required. And I don't know if you remember, but this is pretty rare. Most forces that we've come across require one thing pushing or pulling on another. We've only seen one other example of a force that acts at a distance, and that's gravity. So now we're introducing some other force that is also acting at a distance. Well, if forces are acting at a distance and we want to try to visualize how and where those forces are acting, just like we did for gravity, the other force, we can draw fields. We can represent these forces and how and where they're acting by drawing a force field. So that's what we're going to do. Just like we can draw a gravitational field to show how the gravitational force acts at a distance, we can draw an electric field to show how this electric force acts at a distance. We saw this for the force of gravity. We're going to do something similar for electric forces that come from electric charges either attracting or repelling. All right. Now, team, what's a little more challenging in this scenario is that this force, this electric attraction and repulsion, well, sometimes it does just that. Sometimes it's attracting and sometimes it's repelling. That makes the next set of fields trickier than before. Reminder, gravity was relatively easy. Not easy, but compared to what we're about to do, about 50% simpler because gravity always attracts. That's all gravity can do. But now we're dealing with charge, and charge sometimes attracts, but it also sometimes repels. Okay. So how do we draw these, all right? Let's pretend I have a positive charge, and let's maybe say it's like glued to the screen or glued to the piece of paper that we're working on. Uh-oh, I have my pocket again. Let's pretend this is already here. Let's pretend, everybody, I reach into my pocket and I pull out a little positive charge. We're using our imagination. I pull out a little positive charge, and let's say I put it right here. So the original thing is positive, and I've just pretended to put down a little positive. What direction do you think this little positive is going to go? Is it going to attract toward this red object, or is it going to repel? What do you think? It's going to repel, everybody, because we learned like charges repel. Both of these are positive. Positive charges do not like each other, so this little positive is going to repel away. Let's go again. I'm going to reach into my pocket, so I'm pretending to go into my pocket. I'm going to pull out another little positive. And now let's pretend I put the little positive here. What direction arrow do you think it's going to feel? An attracting force or a repelling force? Team, it's repelling for the exact same reason as before. This is positive, that's a repelling force. I reach into my pocket, I pull out a little positive, I put it right here. What direction is the arrow? To the left, of course, because it's going to repel. Team, any little positive I place on this imaginary line is going to feel a force away directly upward. Any little positive I pretend to pull out of my pocket and plop down on this line is going to feel a force this way. Likewise over here, if I kept going, a little positive right here, it would feel a force down, a force to the right, a force diagonal to the left, a force diagonal down and to the right. This is the force field for a positive sphere. What's the rationale? The electric field arrows, these arrows in blue, they represent the direction of a force acting on a little positive charge placed anywhere on this line. So my mantra, I'm pretending to reach into my pocket, pull out a little positive, and I pretend to drop that positive charge down, and I draw the resulting arrow. If you were thinking to yourself, well, why not pretend to put in a little negative? Couldn't I reach into my pocket and pull out a little negative charge? That's a great question. To be honest, sure, you could, but so that scientists are always talking about the same thing, the convention, what it's almost like scientists agreed to do. Scientists have agreed that the electric force field is always going to be showing what happens if you put down a little positive. We're just making it up, but that way we're not going to be confusing ourselves. If I send an electric diagram to someone in Japan, I want them to be recognizing the same physics idea. So by convention, almost like by tradition, we're always pretending to reach into our pocket, pulling out a little positive, and that way we'll always draw arrows that represent how a little positive charge would move. Team, just like I did for my gravitational video, let's look at a more complicated scenario. Here I have a positive charge, and here I have a negative charge. Let's pretend the red and the blue circle are like glued in place, okay? So they're not moving. We're pretending like they're being glued in place, and let's think about if these lines that are drawn make sense. Spoiler, they do. But why? Let's look at this line right here, this line. Well, if I pretended to reach into my pocket and pull out a little positive, imagine I put that little positive right here. Well, the little positive charge would repel from this thing. So right away, it's going to be like, oh man, I don't want to be near here. I hate this thing. Like charges repel. So it starts getting the heck out of here. But then, oh man, a little more challenging. This little positive charge goes, hey, I like this negative thing. I hate this thing in red, but boy, I do like this negatively charged thing. So it repels from the red, but it also might attract over to the blue one. Oh, maybe a little simpler. Let's pretend I reach into my pocket, pull out a little positive. If I put it right here, oh man, if I put a little positive charge right here, even if maybe it likes this thing, it's so close to this positive, it wants to get the heck away from it. Zoink, it goes flying off to the left. Or if I pretend to reach into my pocket, pull out a little positive, if I put it right here, a little positive charge right here loves negative because opposites attract. So a little positive here would go zoink, it would want to get closer. So just like for the force of gravity and gravitational fields, these can get a little complicated. It's always a little bit of creative thinking. You're always, though, pretending the same thing. You are reaching into your pocket. You're pretending to pull out a little positive. If I put a little positive right here, it wants to get away from this thing, so it starts repelling. If there wasn't this negative charge, it might just go in a straight line. But because there's this negative, which a little positive would like, it might start wanting to go over. I ran out a page over here, but this is a correct diagram because this is showing the force, the attraction and repulsion of little positive charges. Little positives would repel from this thing, little positives would attract from this thing, all right? We are always pretending to drop in little positives. You're going to hear me, if you're in my own class, say that a lot, and it maybe sounds silly, but that's how you remember how to do this. We're pretending to reach into our pocket, pull out a little positive, and we're dropping in those little positive charges. The lines and the arrows, they are representing how that little positive charge would move. Again, if you're in my own class, we'll do plenty of practice. These are the notes that I often give students in my own class. It goes over. It has very similar rules as to our force fields for gravity, that the lines always touch the objects. You want to draw these arrows. But now notice, the force field lines, they show the direction of a force, attraction or repulsion, acting on a small positive charge. So you get good at these by just practicing them. That's my introduction for electric force fields. All right? Thanks a lot for watching.